Hello everyone. Have you wondered how lifting a book from the table or kicking a football involves energy? Today we will deep dive into the very important concept that is Work-Energy Theorem, in which we study and we get to know that how motion and energy are interconnected. This is the very crucial and very important topic in terms of board examinations and competitive examinations like NTSE, Olympiad, etc. And in the end of this session, you got to know that they both work and energy are the same two sides of the same coin. Okay, so let's start. Work, energy, theorem. Okay, so basically, what is work-energy theorem? Here, the first thing that we have to know that when we talk about energy, right? When we talk about energy, we always consider kinetic energy. Why? Because we don't consider potential energy, we always consider kinetic energy, because kinetic energy is directly related to the motion and kinetic energy is related to how work increase object's speed. But potential energy is the energy which is stored due to position or position and height from the surface of the earth. Okay, so always in this theorem we always consider kinetic energy, not potential energy. Okay, okay. What kinetic energy says? Kinetic energy. Sorry. What work-energy theorem states? This theorem states that the work done on any object is equals to the change in its kinetic energy. That means the work done means W is equal to change in kinetic energy, or we can write it like delta KE. Why? Because delta denotes the changes. Okay. Now let's try to understand how this works. Okay. So let's take an example. Suppose there is an object. Okay. This object is moving with a very slow speed, very small speed or velocity. It is moving with very small velocity, and suddenly I apply a force on it, right? Then because of the applied force which is applied by me, it displaces, it undergoes displacement. That means I have done some amount of work on it. Okay. So now the question, there are two questions arises. The first one, if I applied a force, the first question is, if I applied a force, then where does if I applied a force, that means I have done some work. So the question is, where does this work go? And the second question, when I applied a force, I put some amount of energy on this in this object. So the second question is, where has this energy been transferred? So there are two questions in our mind. The first question is, if I have, because this body was moving with a very slow speed and I have put a amount of force and it causes this the force causes displacement, or we can say it undergoes displacement. And when body undergoes displacement because of force, that means there is some amount of work has been done on that body, right? So where does this work go? And the second question, when applying a force or while doing a work done on it, I have put some amount of energy on it. So where has this energy been transferred? So these two questions that comes in our mind. Okay, so let's try to understand these things. The first thing, while applying a force, right? I mean, on careful observation, you can see that when I applied a force, its speed increases, right? Because it was moving with a very small speed, and when I applied a force, its speed or its velocity increases, which leads to increase its kinetic energy, right? So ultimately, the work which I have done on this object causes change in kinetic energy or increase in kinetic energy. All right. So let's take another example. Suppose there is an object. Suppose this is a body of mass 1 kg. Okay, not 1 kg. Take. Okay, let's take 1 kg mass. Okay, it is moving initially with initial velocity of 10 meter per second. Right. U is the initial velocity. We always denote initial velocity by U. Okay. So suppose it is moving with the initial velocity of 10 meter per second, and suddenly a force is applied. Force F is applied on this body, and again its velocity, means final velocity, becomes 20 meter per second, and the mass of that body is remain same because mass is constant. Okay, so now the question is, calculate the work done. Okay, so what we know from the formula of the work done, we all know work done is equal to F dot S, Fs, or Fs cos theta. But in this question, we don't have the data of force, we don't have the data of displacement, and there is no angle is given. Okay, but angle is given because force and displacement are both are in the same direction, so we can say theta is 0 degree, but still we don't have the value of displacement and the force. So for solving this kind of problems, this work energy theorem comes into play. What we have, okay, listen, in the initial stage, its initial velocity was 10 meter per second, right? Okay, and final velocity was 20 meter per second. So initial kinetic energy was caused by this initial velocity, and final kinetic energy was caused by this final velocity. And what we have, we will apply according to work energy theorem. W is equal to delta Ke, means change in kinetic energy. What it means? Means kinetic energy final minus kinetic energy initial. For final kinetic energy, we will consider the final velocity, and for initial kinetic energy, we will consider initial velocity. And what is the formula of kinetic energy? We all know the formula of kinetic energy is equal to half mv square, right? So for final kinetic energy, it will be 1 by 2 mv square, and for initial 1 by 2 m initial kinetic energy, means mv square initial velocity. take 1 by 2 and m common, so v square minus u square. Put the values of mass and velocity is 1 by 2. The value of mass is 1 kg into v square. V square by velocity is 20 square minus 10 square. 20 is a 400 minus 10 is a 100. It will be 1 by 2 into 400 minus 100 means 300, which is equal to 150 joule. Okay, so what we get the work done, which is equal to 150 joule. What is 150 joule? 150 joule is that work done which is required to increase its velocity from 10 meter per second to 20 meter per second. So we can say that to increase the velocity of 1 kg of mass of object from 10 meter to 20 meter per second, we have to put work on it about 150 joule. Alright? Okay, now let's talk about the proof of this theorem. Proof of work-energy theorem. Okay, what we have change in kinetic energy is equal to kinetic energy final minus kinetic energy initial, or we can write it like 1 by 2 mv square minus 1 by 2 mu square. And change in kinetic energy, we denote change in kinetic energy is delta ke. Alright, now let's take half as a common and not half as a common, we will take mass as a common. Okay, take mass common, then v square by 2 minus u square by 2. Alright, so if we rearrange it, m into v square minus u square upon 2, right? So now we get the equation delta ke is equal to m into v square minus u square. Okay, let's take it as a equation 1. Now what we will do, we will on multiplying by common factor, let's take a common factor a for acceleration, right? In numerator and denominator of the equation 1. Okay, so let's multiply the numerator and denominator by equation 1. So this equation becomes m into a, m into a and v square minus u square upon 2a, right? This is the delta ke. Since we all know what we know, F is equal to ma, and from the third equation of motion, what we know from the third, there are three equations of motion where that we have learned: the v equal to u plus kt, f equal to ut plus half a square, and the third one is v square minus u square is equal to 2as. So from the equation third, v square minus u square equal to 2as. If we rearrange it, we can write it like S equal to V square minus U square upon 2A. Okay, so what we get, we can replace this value, we can replace this value by S. So now this equation becomes delta KE is equal to MA is becomes F, and this value becomes S. So finally what we get delta K is equal to Fs means W. So hence delta KE is equal to work done, which we have studied from the beginning. Okay, let's recap this all. What we will learn in work-done theorem, we learn the relation between kinetic energy and the work done. Why we consider kinetic energy? Because kinetic energy is directly related to the motion, and it related to how work increases the speed of the object. Okay, what this theorem says? This theorem says that the change work done on any object is equal to the change in its kinetic energy, means delta K is equal to work done. All right. Okay. So then we take an example of this 1 kg of mass. We know that if we have a problems or calculations like if we don't have the force, we don't have the displacement, then how can we calculate the work done? If we have the velocities or if we have the values of kinetic energy, we will apply work-energy theorem. Alright. So in the proof, what we get what we have done. The change in kinetic energy is equal to kinetic energy final minus kinetic energy initial. Again we solve it, we take a common of m and it becomes v square by 2 minus u square by 2, and again we rearrange it, so it becomes v square minus u square upon 2. And what we know what we have done, then we have multiplied by a common factor a in both numerator and denominator. So this equation becomes ma into v square minus u square upon 2a. We all know that F equal to ma from the second equation of motion. So in place of ma, I have put F, and in place of this v square minus u square upon 2a, from the third equation of motion, I have put S, which becomes ultimately work done. So we prove that the kinetic energy is equal to work done. Okay. So that's all for the work done theorem. Thank you.